So let's talk about regression. We're going to dive a little deeper into some concepts we started to cover in chapter 4 in this chapter 5. So the first thing we're going to talk about are regression lines. The least squares regression line, which is like the regression line really. Some examples of using technology. Facts about the least squares regression line. We're going to talk about what residuals are and how to interpret them. Outliers and other influential observations. Some cautions about correlation and regression. Remember, correlation is not causation. I can't say it enough. The fact that association does not imply causation, see, I said it again, as well as correlation. So I think a great place to start would be like, what is a regression line? So a regression line is a straight line, in this case, that describes how a response variable, y, changes with our explanatory variable, x. This is concepts we covered in chapter 4. Feel free to go back and look at those. We often use a regression line to predict the value of y for a given value of x, especially when we believe this relationship is linear. Again, it doesn't have to be, but in this chapter right now, we're discussing linear correlation. So here's a good example. So we're going to predict the gain in fat in kilograms based on change in non-exercise activity in calories. So as the more calories are burned, more fat is lost, right? This has negative correlation. So we could use this to predict something. We could say, okay, if the change, is 400 calories, what is the expected fat gain? So if the change is 400, right, the expected fat gain might be 2 grams. So let's talk a little bit about straight lines. So when y is our response variable and x is an explanatory variable, we get a straight line relating y to x in an equation of the form y equals ax plus b. Now I know what you're all thinking. Again, thinking back to college algebra, you were told it's y equals mx plus b. Well, statisticians, of course, liken to be a little different, do things differently. So in this case, a is our y-intercept and b is our slope. Again, slope is not our correlation coefficient. So here, like I said, b is the slope and the amount by which y changes as an x increases by 1 unit, right? Like rise over run, that's slope. And a is our intercept, and that's the value of our y when x equals 0. Because if I plugged in 0 for this x, you see all that's left would be our a. So the least squares regression line is what I'm going to talk about next. But first, what we want to do is plot our lines on a scatter plot, right? We're going to use the equation to find the predicted y for 2 values of x, because you need 2 points to draw a line, right? If I have 1 point, I could draw any lines between it. But if I have 2 points, I can draw just only one straight line. So the least squares regression line of y on x is the line that makes the sum of the squares of the vertical distances of the data points from the line as small as possible, right? We're just minimizing these distances. Like it's the method of least squares. We want to have the smallest sized squares when it comes to that line. So the equation for the least squares regression line, again, we're going to be doing this in R. We are not going to be calculating this by hand. But I have y is a plus bx. My slope is going to be my R value times the standard deviation of my y value over the standard deviation of my x. And my intercept, again, all I'm doing is taking my original equation and solving for a. So I subtracted that bx. I moved it over to the other side. And that's b times x, which is our x bar, which is the mean of our x values. Y bar is the mean of our y values. So let's take a look at comparing how to do predictions on our regression line. So for our non-exercise activity example, we found the least squares regression line to be y hat. So y hat, that's our mean, that's our predicted mean. Did I just misspeak? Yeah, no, I don't mean mean. That's our predicted value. So I have 3.505, that's my y-intercept, minus 0.0034x. So this has a very small slope, right? But slope is not our r. It's important to remember. So y hat's what we predict to be the fat gain when you have more calories of non-exercise activity. I guess that's calories burned. I think it is. So let's say we know someone has an increase of 400 calories. What will we predict for their fat gain? We estimated before, we said it's right around 2, but why don't we calculate that to make sure that is correct? So I would substitute in 400 for x. Remember, this is our x-axis, so this would be our x variable. So I'd have my y-intercept minus my slope times 400. That gives me 2.13 kilograms. So our estimate of 2 was good, but just not perfect. So here are some quick facts about the least squares regression line. So you always need to make sure that you distinguish between your explanatory variable and your response variable. That is critical. There's a close connection between correlation and the slope of the least squares line, but they are not the same thing. Not the same thing, though. They are going to have the same sign, which is really nice. Positive slope means you've got a positive correlation. Negative slope means you have a negative correlation. Along our regression line, a change in 1 standard deviation in x corresponds to a change of r standard deviations in y, and you could kind of see that being the case based on the formula above. Our least squares regression line always passes through the mean of x and the mean of y. And our r, like I said, describes the strength of our straight line relationship. So the square of that r value, our correlation coefficient r squared, is called the proportion of variation in a variable. And what it is the percent of variation in a variable that is accounted for by the best fit line. So like, let's say I had r as 0.5. That's a weak positive correlation. That gives me an r squared of 0.25, which means about 25% of variation in our data is accounted for by the best fit line. So that means that 75% of our variation is due to other factors, right? It accounts for 25% of the variation in that best fit line. Let's practice interpreting another r squared value. So let's take a look at this data set. So this is the data set between math scores and age, right? There's this positive correlation. That makes sense. Your scores should get a little bit better as you get older and learn more math, especially when you're between 5 and 7. So the r squared for this data set is 0.07. That means that 7% of the variation, like the jumpy aroundness in this data, is accounted for by this best fit line, but 93% of it in converse must be due to other factors. So, like I said, the square of our correlation r squared, right? It's the fraction of variation in the values of y that's explained from the least squared regression of y on x, right? Like, so that's just r squared, right? We can find a regression line for any relationship between two quantitative variables, but the usefulness of this prediction depends on whether it's a strong relationship. If I had such a weak relationship like this example, right, this is a really small proportion of data that's occurred by the value. So I wouldn't want to use age as a predictor. Like, this would be a bad predictor of outcomes. R squared near 0 means a weak linear relationship. R squared mean 1 means a strong linear relationship. This is when you'd want to use that for prediction, to predict a value. you wouldn't want to do that for a weak correlation. Note that with R squared, we lose information about the direction of the correlation, right? If I just gave you an R squared and I didn't tell you an R, you wouldn't know whether R had been negative or positive, because R squared, a positive number squared is positive, a negative number squared positive, as we learn whether it's a positive or a negative correlation. Last thing I want to touch on briefly in this video is residuals. Okay, so what a residual is, let me get all this up here. So a residual is the difference between the observed value of the response variable, i.e. like the actual outcome, and what was predicted, so what's on that best fit line. So the residuals are the difference in y from our outcomes, our observed data, to that line of best fit. Like all of these would be residuals, right? And there's a lot of them. So residuals are like leftover variation that isn't accounted for by that best fit line. And if I just wanted to plot the residuals, right, means, so the residuals, here's a residual plot. We plotted the distance from the residuals. The residuals always have a mean of 0. We're always going to have an even amount above the line and an even amount below the line. So a residual plot is a scatter plot of the regression residuals against our explanatory variable. And you always want to look for random scatter around the 0. And it helps us assess how well a regression line really did fit the data. But the most useful of all things is really just going to be our R value and that R squared value. That's what you really want to focus on when it comes to how good a regression line fits the data.